So this is ADE Fall 2021, problem three. It's a pretty long problem, so let's just get into it. Um, we're asked to show, using separation of variables, a solution of this form. So assuming this, the left-hand side of the PDE becomes this, uh, and then the right-hand side is this, r times rho prime minus rho divided by r squared. And the t can come out because it depends only on time. Then this can be simplified. So this is rho prime minus uh, r rho double prime minus rho prime. The rho primes cancel and we're just left with this. Sorry, this should be a plus. So the right hand side just becomes um, rho double prime times t divided by just r. So then the entire PDE just becomes this. Rho over r times t prime is equal to rho double prime over r times t. Rearranging, we get this. So as is usual with separation of variables, we get an expression on one side of the equation, which depends only on r, while the other side depends only on t. So it follows that both expressions are constant, let's say negative lambda. Then solving for the time component amounts to solving this ODE. And it's clear here that the solution is of this form. So now let's go to the radial component. So before we actually write down the ODE satisfied by rho, let's first determine some initial conditions. So by hypothesis, C at time zero is this. Uh, but we assume that C takes on this form given by separation of variables. Um, so this is equal to this, T at time zero. Um, so if you look at our solution for the time component, we see that T of zero appears as a multiplicative factor in the solution for C. So we can just assume that T of zero is not equal to zero. Otherwise, we would end up with a trivial solution in C. So that's all to say that we can divide by T of zero. And then multiply by R. So then it follows that rho of zero is equal to zero. So this is our first side condition. Uh, then to get another one, we can use the boundary condition on the radial derivative of C. We were given this in the hypothesis, right? And we actually computed this derivative at the start of the problem. This was again this. And again, we can use the fact that T of zero is non-zero and this identity holds for all T. So we can just divide both sides by T of T. Zero is unchanged. And we can also get rid of this minus sign. and we'll still have 0 on the left-hand side. So then when we evaluate this at r equals 2, we get this. So we get an initial condition, or sorry, a side condition, which we can write like this. Right, so to solve for the radial component, we solve this ODE. So this is a Stern-Liouville problem, and that fact will come in handy towards the end of the problem, but it's useful to mention it now. Um, so now to solve this, we note that this is a linear ODE whose characteristic polynomial has roots plus or minus square root of negative lambda. So we have a few cases. Let's first consider lambda negative. Then our solution is of the following form. Then applying the initial conditions, we get the following system. The first condition gets us C1 plus C2 is equal to 0. Then the second condition gets us a slightly longer statement. Sorry, this is, yeah, negative. So we can rewrite this by just subtracting this quantity. So we end up with 0 on the right-hand side of both equations. And we can rewrite this uh, using matrices. So it turns out since lambda is non-zero, these two terms are distinct from one another. So if you were to compute the determinant, it ends up being the difference between these two terms, which ends up being non-zero. And that tells us the matrix is invertible. So we only end up with the trivial solution, right? So we can disregard this case. The second case, lambda is equal to 0. And here we end up with the following solution. So the first condition gets us that C1 is equal to 0. So rho is just of this form. And it turns out the second condition gets us no useful information. So uh, we get this solution. In the third case, lambda is positive. So rho is of this form. Applying the first condition, we get rho 0 is equal to 0. Uh, the sine term vanishes and we're just left with 0 is equal to C1 times cosine um, of 0, which is 1. So this means 0 is equal to C1. Uh, so that means this cosine term vanishes and rho is just equal to C sine of square root lambda r. Then applying the second condition, we get C sine of square root lambda times 2. is equal to 2c times square root of lambda of cosine of square root lambda times 2. The c's cancel. Uh, then dividing through by cosine, we get tangent of 2 square root lambda is equal to 2 square root lambda. And here, we again want to use the fact that this is an SL problem um, to conclude that there are infinitely many solutions to this equation. So putting case 2 and case 3 together, we can enumerate our eigenvalues as, let's write it like this. We can enumerate our eigenvalues by natural numbers, including 0, is equal to 0 union with the solutions to this equation. Right? And the what we'll make use of later is the fact that the eigenvalues to Stern-Liouville problem are increasing. So we can actually enumerate the eigenvalues in increasing order. So now our eigenvalues are of this form. Again, for n natural numbers including 0, where lambda 0 is 0. The first solution is r for n is equal to 0. Right, that comes from case 2 here. And for n greater than 0, we have this. And then we can enumerate the solutions of the time component. Remember, this was given by e to the negative lambda t. Now that we have our eigenvalues, these end up being the following. Right, and this constant solution comes from the fact that, again, lambda 0 is 0. So first eigenfunction for time is just a constant. Then we can express C as a series of these eigenfunctions. So we can just express it like this. We can pull out the 0th term and write the rest of the terms like this. Sorry, these should have coefficients in front of them, which are to be determined. So here, t of 0 is constant, right? This is 1. Rho of 0 is r, so divided by r, you get 1. So this is just a0, a constant, plus the rest of these terms. So now when we take the limit as t approaches infinity, this limit doesn't see the first constant because it doesn't depend on time. So this is just applied to the rest of the terms in this series expansion. On here, we use the fact that this n ranges over n greater than or equal to 1. And for n greater than or equal to 1, our eigenvalues were the positive solutions to this equation. Right? These are coming from case 3. So all of these eigenvalues are positive. So these are decaying exponentials because of this negative sign. So as t approaches infinity, um, these all approach zero. So C infinity is equal to the first coefficient in this series expansion. So now in order to actually compute this first coefficient, we want to make the following observation. So we can define the usual integral inner product as follows. And since these eigenfunctions come from a Stern-Liouville problem, they satisfy an orthogonality relation times some constant because we can't ensure that they're normal. The problem is when we look at this series expansion, we don't exactly have just rho by itself. We have rho divided by r. So in order to take care of that, we define a modified inner product. Where we multiply the integrand by r squared. Uh, then when we look at this inner product on the rows divided by r, we get the following. So this r squared cancels out the division by r on both terms, and we're just left with the usual inner product on the two eigenfunctions. Right, so this is all to say that with respect to this modified inner product, these terms in the series expansion satisfy an orthogonality relation. So then we can compute the first term in this expansion as follows. If we take this expansion and evaluate it at time 0, this exponential goes to 1. We're left with this. And let's modify this slightly. Recall that rho 0 divided by r times t0 is just 1. So a0 is really equal to a0 times rho 0 divided by r. Then we can inner product both sides with rho 0 of r with the modified inner product. And we get this. This term is rho n divided by r. So we get this. On here, this index ranges over n greater than or equal to 1. So we can use the fact that these are orthogonal to say that all the terms in this sum vanish. So we're just left with this and this. So we can solve for a0 just by dividing. Then just expand this using the definition of this modified inner product. Again, rho 0 of r is just 1. So we're just left with this. And the denominator is 1 times 1 times r squared. So we're left with this. And at this stage, we want to use the fact that CR0 is the indicator function on the interval of r greater than 1. So this integral just becomes the integral from 1 to 2 of r squared. Right, so both sides have the same primitive. This is 8 over 3 minus 1 over 3, and this is 8 over 3. So this ends up being 7 over 8. So this is the value of C infinity. So now for part B, we're asked to show that the difference between CRT and C infinity can be bounded above by some decaying exponential. So by the work that we did in part A, C has the following series expansion. And then the main result of part A was that C infinity is actually just this first coefficient. So this difference that we're interested in is just the rest of the terms in this series expansion. So we're really interested in just bounding these terms. So here we can use the triangle inequality. And we can pull out this exponential because uh, it's non-negative. So again, we're going to use the fact that these eigenvalues come from a Stern-Liouville problem. So for Stern-Liouville problems, the eigenvalues are strictly increasing. So we have the following relation. Then we can use the fact that the exponential is monotone. And we're not worried about lambda 0 here because the index runs over n greater than or equal to 1. So this inequality implies this for each fixed t positive. So this means we can bound each of the terms in this sum independently using this maximal exponential. Right, and the good thing about this is that this term doesn't depend on n. Right, and so now we have a bound precisely of the form specified by the claim. And the problem doesn't ask for a specific value for alpha, but here we're writing alpha is equal to lambda 1. And if we want a specific value, we can go back to the work we did in part A, right? These eigenvalues come from solutions to this equation. And lambda 1 was the least of those solutions. So it turns out if you were to solve this numerically, lambda 1 ends up being about, let's see, this was about 5.04768. Right, so that's part B.